The algorithm I'm going to describe is called Fortune's algorithm. There are other analog N solutions like divide and conquer strategies, maybe other algorithms exist as well, but Fortune's algorithm is a well-known algorithm, and you can find implementations of it, even some applets that describe the Fortune's algorithm on the web. It's a plane sweep algorithm. So we are going to construct the Voronoi diagram incrementally by considering the points either from left to right or from top to bottom or bottom of whatever you want to sweep the plane. But so we are going to have a sweep line, and we have, let's discuss the algorithm now. So this is our sweep line. And here in Fortune's algorithm, we cannot actually use a regular plane sweep algorithm, because here you say that you usually assume that when you come to this sweep line L, you have computed the Voronoi diagram for the points above this diagram, right? And the diagram should be correct above this line. For example, as the status structure, you can, so what are you going to store as the status structure? So your events may be your points. So event queue is simple. They may be points. You go from point to point, sorted in terms of their y coordinate. But what is your status structure going to be? For example, the edges of the Voronoi diagram that we intersect with, maybe. Okay, these are the edges of the Voronoi diagram. You can maybe store that, but the problem is that some of these edges cannot be identified without actually considering points below this line. Okay, there may be certain points just below this line which define the edge of the Voronoi diagram, or even some vertices here, some vertices of the Voronoi diagram may be identified. So this may be a vertex, for example. Okay, but this vertex is due to this point, which is below the sweep line. So we don't know, at the sweep line, we don't know everything about our Voronoi diagram above the sweep line. So a vertex like this, which when the sweep line comes here, we haven't identified this vertex yet. Okay, so the sweep line came here, but this vertex is going to appear due to a point which is below the sweep line, which is not processed yet. So we cannot, our sweep line strategy is actually, the sweep line is not going to know all about the Voronoi diagram above itself, so above the sweep line. But, I mean, can't we do anything? Now we are going to ask, is there a certain region of the Voronoi diagram that we can be sure about? Okay, which part of the Voronoi diagram above the sweep line can we be sure that that region, for example, a point here, a point Q, I know that it cannot belong to a site here, it has to belong here. So for which points can I say that? For example, I cannot say for this point that, oh, okay, this point is, its site is this. I cannot say that because just below the sweep line, there may be another site which is going to claim that point. However, what we can do is, we know the sweep line has a certain y coordinate, right? So it has, so the y coordinate of the sweep line, we know that. For example, look at this midpoint here. Okay, between this point. Okay, I cannot say anything about these points, maybe, because there may be other points here. But a point here, for a point Q here, if its distance to the sweep line is larger than its distance to any side here. In other words, if it's closer to a side, it means that there cannot be any side below it. I mean, I know that its side is, it's the side that this point belongs to is above the sweep line, should be above the sweep line. For example, let's just look at this vertical line here, this vertical line here. I know that half of the points above this vertical line belongs to that side. There cannot be, because the distance of this point, the distance of a point here is, for example, it's xp yp. It's yp minus l, yp minus ly is greater than this if this is xs ys. If yp minus ly is greater than ys minus yp, then I know that this point, I mean this distance is, if this distance is shorter, I know that there cannot be any point which can claim this point. Its side is going to be this one. Now, here's the question. For a given site, xs, ys, what is the, how does the locus of the points, I mean, how is the point set that belongs to, just forget about all the other sites first, okay? Just think about the sweep line and any site that can appear under sweep line. There can be just hidden sites waiting for us. There may be many sites here just trying to claim these points. Okay, we don't see them yet. These are our enemies. They're waiting above the, so this is the enemy line here. We don't know about them. But what is the, how does the, which points can we exactly say belong to xs, ys? And how does the shape of these points, the collection, it's called the locus of these points, how does it look like? If you look at this line only, I mean, half of this line is going to belong to that. But what about a point here? What you need to do is this, right? So here is the, in order to find all such points, let me just name them xq, yq. In order to think about how the shape of these points look like, you need to do this, right? The distance between xq minus xs square plus yq minus ys square. So this is the distance, the Euclidean distance between the point and the site, right? And the distance between the point and the line, what is it? It is yq minus ly, right? This is the distance of that point to the sweep line. So what should happen is that this distance should be less than yq minus ly, right? So for all those points, for all those xq's, yq's, if this holds, I can even say that less than or equal to, if this holds, that xq, yq belongs to, for certain belongs to that site, right? So this is, the question is, what does this equation, what does this inequality, what kind of a shape it defines? Is it a circle? If you just take the square of both parts, so it's going to be xq square minus 2xq xs plus xs square plus yq square minus 2yq ys plus ys square minus yq square plus 2yq ly minus ly square is equal to 0. I mean, if I'm just interested in the boundary, I'm just trying to see how the boundary looks like. This is my boundary equation, right? Here, some terms cancel out each other, so yq square goes. Okay, so and some things are constant. I know that my site's coordinates, so this is my constant. I can get rid of the constants as well. Ly square, I know ly as well, so I can just collect them together and say C, if you wonder about what the equation is going to look like. So equation is something like this. And ys square is also a constant, so I can get this one as well constant. So xq square minus cxq, let me name C1, okay, constant 1, minus C2 yq yeah, actually this yq, the C2 is going to include these ys and lys, okay, plus another constant is equal to 0. So the equation is going to look something like this, right? By by looking at the unknown terms, xq's, yq's are unknowns. So it's quadratic in terms of the x coordinate, and it's linear in terms of the y coordinate. So it's not a circle. It doesn't look like a circle. What do you know what this equation is going to look like? Yeah, it's going to be a parabola. Okay, so what will happen is that we are going to have, this is going to be a parabola. Its lowest point is going to be the midpoint here, and it's going to be something like this. Okay, so all the points within this parabola, we are going to know for sure that it belongs to this side. And any other point here can be claimed by other sides here. So we know for certain that these points cannot be claimed by anybody, any enemy behind the line. So for each of these sides, we are going to have a different parabola. Okay, for other sides above this line, we are going to have another parabola. Okay. And the parabola, in the degenerate case, when the site is just appeared on this sweep line, the parabola, the degenerate parabola is going to be just a line that goes up. Okay, so these are the points on this line are going to be closer or equal to this thing here, and any other point here is going to be closer to the sweep line. So the parabola starts with a very thin parabola, like it's going to be a line like this, and as the sweep line goes down, the parabola is going to get wider and wider and wider as this line goes down. And as you can see, several sides are going to have different parabolas themselves. And what we are going to define is here, this looks like here, the intersection of parabolas that are closer to this enemy lines is actually looks like a beach line, okay? If you think about these like waves, okay? So their intersection, if we take the parabolas which are closest to this, if we take parts of the parabolas which are closest to the sweep line, we get ourselves a shape like this, a sequence of arcs. And in the Fortune's algorithm, this is called the beach line. Okay? And we know the Voronoi diagram above the beach line for sure. Okay? The Voronoi diagram above this beach line is known for certain. Nothing can change here. And the beach line is x monotone, meaning that any vertical line intersects this beach line at one point. It's by definition like that, because we said that, there may be other parabolas here. For example, there may be another side here with this parabola, but we pick the parabola which is closest to the sweep line. Now what will happen is that our study structure will be this beach line. As we move our sweep line, we are going to, these beach lines are also going to, there may be new beach lines appearing. So the structure of this beach line is going to change as we move the sweep line lower and lower. And there may be interesting things. For example, a single parabola may contribute to beach line in two different places. If I have a parabola parabola like this, for example, it's going to contribute to the beach line here and here. Okay, so a parabola, if there's a side here, for example, a parabola may contribute in two places, and this will happen actually when we encounter a side on the sweep line. When it starts its parabola, it's going to hit an existing parabola, and it's going to divide the existing parabola into two different arcs, and the beach line structure is going to change. So as we move the sweep line, we are going to maintain this beach line, and we don't need to actually maintain we don't need to store the exact parabola equations. Here, all we need to know is which sides. For each of these arcs on the beach line, we need to know which side this arc belongs to. So we are going to store the sides from left to right. Our study structure is going to be a binary search tree. Why is it going to be a binary search tree? Because when a new site appears on this beach line, I need to efficiently identify which parabola it's going to break into two. So where it's going to appear on this beach line, I need to find this efficiently. So given an x coordinate of this new site, I need to identify the arc that is going to intersect with. And this is going to be done by looking at this binary search tree. Our binary search tree is going to have the sites at the leaves, and also I need to, in the intermediate nodes, I'm going to have the neighboring site information. This is neighbor to this one, because to identify which way to follow, we need to identify these intersection points of these arcs, and these intersection points actually can be identified if you just know Ly and the sites. If you know these two sites, the coordinates of these two sites, and if you know the y coordinate of the sweep line, you can find the intersection point. I mean, this intersection point is the point which is equal distance to both Ly, this side, and the other side. Okay, so this can be uniquely identified. So this is like the center of the circle, right? Which is, since it's equidistant, if I have these two sides, and if I know the Ly location, sorry, it cannot be, I don't know this x coordinate yet. I know just the Ly, but still it can be found. I need to draw a circle that passes through these sides, and the circle cannot penetrate this Ly. It can be tangent to this Ly. After finding these, you can find the intersection of these parabolas. And the intersection of these beach lines, these parabolas, are called breakpoints. Okay, so these are like waves, and these intersection of these arcs, the sequence of arcs. Here, this intersection point is called the breakpoint of the beach line. And each intermediate node in my study structure is going to denote a breakpoint between the neighbors, and these breakpoints will help me to navigate in this binary search tree. For example, if a new site appears here, I'm going to look at the root breakpoint, which is, just imagine the arcs are divided into two. If it's a balanced binary search tree, half of the arcs are on the left subtree and half of the arcs are on the right subtree. So this is the center breakpoint. What I need to do is I need to compare the x coordinate of my new event point with the x coordinate of the center breakpoint. If it's left, I need to follow the left subtree. I'm going to look at these waves, these beach lines, these arcs, and I'm going to look at the middle of them. So it's just binary search on the breakpoints, and at the end where you end up is the leaf you end up is going to be the arc that this new event point intersects with. Now, here I mentioned the term breakpoint, the two arcs that intersect at this point. There's a very important property of this breakpoint, which is, this breakpoint is equidistant to two sides, right? So think about Voronoi diagram. What is equidistant to two sides? The edge of the Voronoi diagram is equidistant to two sides, right? So as the sweep line goes, as this beach line progresses, as this beach line change its shape, a breakpoint here is actually tracing out an edge of the Voronoi diagram. Okay, if for example this breakpoint comes here, if this breakpoint moves like this, okay, as the sweep line goes down, if this breakpoint moves like this, it means that the points here are equidistant to this side and this side. It traces out an edge of the Voronoi diagram. So the breakpoints, if we trace them, when we move the sweep line continuously, if imagine there are no discrete event points, you are continuously moving your sweep line like this. When you're continuously moving your sweep line, your parabolas change their shapes because one of the constants here is Ly square. Okay, so the Ly, as Ly changes, your parabolas change their shapes. And as they change their shapes, the breakpoints, they move. Sometimes breakpoints move towards move down. Some breakpoints may move up. Okay, and these moving and up, these breakpoints, when they're moving, they're actually drawing the edges of your Voronoi diagram. Okay, if you have, for example, a graphical program to actually simulate the continuous movement of the sweep line, and you just trace these breakpoints, they will just draw the edges of your Voronoi diagram. So it's a very nice property. I mean, if you look at these breakpoints, they correspond to the edges of your Voronoi diagram. What about the vertices now? And what happens when a new site, let's get back to this problem. I said that breakpoints trace out the edges of the Voronoi diagram, but what happens when a new site just appears? Okay, this is on the sweep line. A new site just appeared here, and a parabola appeared due to this new site. What happens is that there are two breakpoints to the left and right here. There are two breakpoints starts emerging. So if these are edges, which edges? And actually, if you look at this, an important property here is that this site corresponds to a face of the Voronoi diagram, right? Each side is a face of the Voronoi diagram. And each parabola here is associated with a site, which is associated with a face. When a site, when an arc here, when a parabola here intersects with another parabola in two regions, I trace out starting edges between these two faces. But two faces share exactly a single edge, right? In the Voronoi diagram. If you think about the geometry of the Voronoi diagram, the equidistant, I mean, by definition, they share a single edge, because what happens is that if there are two sides, there is a bisector between them. That bisector, part of that bisector is going to be an edge. It cannot be two different parts, cannot be two different edges of the same face. So there's a single edge there. And here what happens is that both this breakpoint and this breakpoint are tracing out the same edge. But it happens something like this. When the site appears, I start tracing out my edge somewhere in the middle of the edge. It may not correspond to a vertex. And one breakpoint traces out the edge in this direction, and the other breakpoint traces out the edge in this direction. So at that point, when I had a degenerate parabola, both breakpoints were at the same point, this intersection point. And as sweep line moves, one breakpoint moves this way, the other breakpoint moves this way. As the parabola gets wider, they are moving in different ways. And this is what exactly happens on the Voronoi diagram. The edge is traced this way. This is one breakpoint, and this is the other breakpoint. Now, the difficult thing is that this edge between these two sides is actually not connected to any part of the Voronoi diagram. Without a vertex, I need a third edge to connect this other edge, right? Because, I mean, this is just an edge that just started, and it's not connected to the Voronoi diagram at this point. So what I need is, I need a vertex to where this edge stops. So at a vertex, this edge is going to be stopped tracing. We are going to stop tracing this edge at a vertex. That edge is going to disappear at a vertex, because we don't have discontinuous edges. I mean, edges is not an edge goes here, it disappears and it continues like that. There's Voronoi diagrams, there's no discontinuity. So when we start tracing out an edge, and when an edge stops at a vertex, that edge disappears. It doesn't appear anymore. So remember the vertex property of Voronoi diagrams. A vertex of a Voronoi diagram is equidistant to three sides, right? So this is called a circle event in the fortunes algorithm, in which if there are three sides, so what will happen is that when we are tracing these breakpoints, sometimes a parabola, when we go down, 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 a parabola may completely disappear from the beach line. And at the point the parabola disappears, what will happen is that, so let me draw it here. Let me show you how the parabola disappears. Originally, there were three parabolas, three neighbor parabolas like this, okay? So let me name them I, J, K. And as the sweep line goes, this I and J may go lower, and based on the locations of these sites, for example, this one may be here, this one may be here. In the next iteration, what may happen is that I and K, so it may be something like this. So this was J, okay? This is I, this is K. So J, the parabola J may disappear from the beach line as the sweep line goes down. I and K get wider and wider, and they consume this. And at this point, parabola J is going to go up in the next iteration. It's going to completely disappear from the beach line. And what happens at this point is that this point is equidistant to I, J, and K. And also, if this is Q, it means that it's going to be a vertex of the Voronoi diagram. And a very good property of this circle is that I also know that this circle is tangent to this line. Why is that? This is the front of the beach. Front of the beach is what? It's equidistant to Ly as well, right? This is how we define these parabolas. The parabolas that are defined based on. So what we have here is that we have a circle which, and there are no other points inside the circle. So there are 3 points on the circle, and this Q, therefore, is going to be a vertex of this Voronoi diagram. Now, such events, so this is actually, as you can see on our sweep line, we don't have any site on our sweep line. This is an event. Something happens, a parabola disappears. But imagine if our events were originally just the sites. Okay, if the points were our events, we will be unable to detect this event because on the sweep line here, there is no point. It's an event. This circle touches the sweep line at this point, but there is no specific event on the sweep line at this point. There is no site. In this event I just drawn, the sites are, all 3 sites are up above the sweep line, and something disappears, something changes on the beach line, but this change is not due to a new site here. This change is not due to a new site on the sweep line. This change is due to this circle being tangent, the circle which is defined by these sites I, j, k being tangent to this sweep line L. So therefore our event Q, unfortunately, is not going to be static. The events are not only going to be the sites. There are going to be 2 types of events in our event queue. Site events, in which a new site appears and a new parabola is inserted into the study structure, and a circle event in which a parabola is going to disappear from our study structure. So sometimes parabolas are going to enter into this beach line, and at this event a parabola is going to disappear. So, and this circle event is going to be the event which we are going to add a vertex to our Voronoi diagram. But now the problem is, how do we detect these circle events? Okay, I mean, when are we going to add this event to our event queue? It's not going to appear magically in the event queue as a circle event. We need to proactively insert that event into the queue. So unless you detect it, you'll never be able to process these events. One way, the solution is, whenever 3 arcs appear as 3 neighbors on the beach line, there's a potential circle event relating to these 3 arcs. Okay? So I say potential. It may not be for certain a circle event, meaning that if at any point on my beach line, if there are 3 neighbors, it's possible that the middle neighbor is going to disappear. It's possible. But the possibility may be introduction of another site that, I mean, the middle arc may disappear not because of a circle event, but because of another parabola appearing, another site appearing. So what will happen in our algorithm is that we are going to insert our queue some potential circle events, which may be false alarms. I mean, that circle event, actually, this disappearance due to this line may never occur. So whenever we insert a new parabola here, what happens is that when this new parabola is inserted, 3 arcs becomes neighbors, but these 3 arcs are not this one and this one and this one. Since these 2 arcs to the left and to the right of this newly inserted site, it belongs to the same site, it's not a circle event. So to be a circle event, we need 3 sites, right? So to be a circle event, we need 3 sites. So when this arc appears here as the middle arc, if this is I, this is J, and this is K, this is not going to be a circle event because I and K, they belong to the same site. These 2 arcs belong to the same site. But is there any other, with the introduction of this new site, is is there any potential circle event? Can you identify a potential circle event? One is this. If there was another parabola here. So if there was a parabola here, what happens is that J, K, and this other parabola M are all, so I mean this new J is the new one. So if the newly inserted arc is the leftmost arc, when it comes, it appears as a leftmost arc, so J, K, and M are all three arcs belong to different sites. So it's a potential circle event. Potentially, this K may disappear somewhere below here. We cannot guarantee this, okay? We cannot guarantee that it's going to disappear, but anyways, we insert it into the queue. So what happens is that when a site disappears, when we delete a site, so in our study structure, in our tree, we also put links between these arcs and their representation, their circle events, potential circle events in the queue. If this arc is deleted due to some other event, we also delete the associated circle event in the queue. So the event queue is really interesting. I mean, some events can be deleted without being processed. If we determine that this is a false alarm, if we determine a circle event to be a false circle event by the disappearance of that arc due to some other reasons, we delete the corresponding circle event from the queue. But if we reach that circle event during the progress of sweep line, it means that it is really a circle event. Okay, so this is how the algorithm, it's a really complicated algorithm. Even, I mean, again, this is an anecdote, I mean, this is a story from the informatic Olympiads. I mean, these are really hardcore programmers that do programming, I mean, that can write 300 lines of code in 5 minutes, okay? These are programmers like that. And this fortunes algorithm, one of the international Olympiads our students told me about in one camp, it was in IOI, International Informatics Olympiads. They were discussing about Voronoi diagrams. And when they talk about fortunes algorithm, everybody said, forget about implementing fortunes algorithm. I mean, it's really difficult implementing fortunes algorithms, even difficult to guys in informatic Olympiads. So as you can see, the event queue is really dynamic. There are lots of things to add, delete, link with each other. And the beach line is actually abstract. We don't actually store the beach line. We store these sites and the breakpoints, and associating these breakpoints with the edges of the diagram and inserting vertices is really difficult. But if you don't implement it, it's easy. I mean, at least you should understand it, okay? So why it works and how it works, you should understand the fortunes algorithm. And if you really need to implement it, actually, maybe you cannot do it in half an hour, but you should be able to implement in 2 or 3 days, okay? If spending 2 or 3 days, all these, they may be tedious. I mean, these small parts may look tedious, but they are not unsolvable problems. They are problems. The solution is given. So by working out the details, you should be able to implement it. So the final algorithm becomes something like this. And in the book, it also, when describing the algorithm, the book also proves the correctness of the algorithm at the same time. So saying that, for example, the only way an arc appears on the beach line is due to a site event. Meaning that without coming to a new site, no previous parabola can reappear again on the beach line. We need to prove this, okay? For example, because when we are going to add some new things to our study structure, we need to know when this is going to happen. If our study structure can change in the middle of nothing, I mean without the site event, then we have a problem. So we need to first prove that a new arc on the beach line can only appear when we encounter a site event during sweep line. So when we encounter a site like this, this is the only way that it's going to appear, an arc is going to appear is this, okay? And an arc can only disappear also, either it can disappear through a circle event, and also when a new arc appears, it can also disappear due to that. But actually, it's the only way it can disappear is through a circle event. So they also prove that. Okay, an arc can only disappear with the circle event. So it cannot disappear with other events. So this is what I said 10 minutes ago is incorrect. I mean, when an arc disappears, it always disappears through a circle event. So first, the book proves the sufficiency of these events. Okay, so we need, when we are designing an algorithm like this, we really need to show, since the event queue should contain all the necessary events. When something changes, we need to detect it as an event. And the book first proves that both the site event and circle events are the only two possible events that the beach line can change its structure. And then the breakpoints on the beach line, they correspond to edges, and the circle events, they correspond to vertices. And this tracking these edges and vertices and creating them when we encounter them, we create our Voronoi diagram as a doubly connected edge list. First, it's going to only have the vertex and edge records. It's not going to have face records because we create an empty doubly connected edge list, and we start inserting edges to it with the breakpoints, and we started adding vertices to it, to the circle points, circle events, and at the end we need to process it to detect the faces. Okay, and at the end, this algorithm, since this study structure is a binary search tree and balanced binary search tree, it can answer queries in log n time, and at the end we are going to have an n log n algorithm. Also, we need to say that the number of circle events and the number of site events is n. Oh, and we already know that. And the number of circle events, we need to maybe prove that in order for the complexity. The number of circle events cannot be, it should be linear. We need to also prove that. The number of circle events is linear. And it can actually be proven like this. The number of arcs on the beach line can be at most 2n minus 1. Why is that? Because each new arc that appears here can divide an existing arc into two, okay? And we cannot, so each site here can correspond to at most two different arcs on the beach line. Since I can have since I have n sites, I can have at most 2n arcs here. And since the circle events are associated with the disappearance of arcs, I cannot have I cannot have a quadratic number of circle events. Okay, so this is how we also prove the linearity of the circle events. So at the end, the event queue in total is going to have linear number of events, and since in each of these events I access my search structure in log n time, at the end I'm going to have an n log n complexity. So the fortunes algorithm may compute this in O(n) log n time. Okay, I'm going to, there may be some degeneracies like 4 points being on the same circle. In other words, a vertex belonging to 4 sites. And these can be, since there are going to be 2 different circle events associated with it, okay, because we insert the circle events as triplets, okay, for each triplet of arc we insert a circle event. It means that for another triplet we add another circle event, but these 2 circle events coincide, okay, the center of these 2 circle events are the same center. So at the end, what we may have is, we may have two vertices in our Voronoi diagram, two vertices at the same xy coordinates, one vertex associated with three of them, the other vertex associated with the other three. But such vertices can be found after post-processing the doubly connected edge list. You can find whether there are duplicate vertices like this. If there are duplicate vertices, you can just merge these vertices into a single vertex. So such degeneracies can be detected in post-processing, and we can get a correct doubly connected edge list. In the last couple of minutes, I'm going to just mention about Delaunay triangulation. The dual graph, of the Voronoi diagram. What happens how do we construct the dual of a Voronoi diagram? What we do is each side becomes a vertex. Now, in the Voronoi diagram, the sides do not appear. I mean, the sides are just like the centers of these Voronoi cells. The vertices are different from sides, right? Now, in the Delaunay triangulation, the sides become our vertices, and we connect two vertices, we connect the two sides if they share a Voronoi edge. Okay, so this is how we construct a dual graph of the Voronoi diagram, by connecting neighboring sites on the Voronoi diagram. And this, if you do this dual graph of Voronoi diagram is a triangulation. Okay, since it's going to be a triangle, you can prove that. And first, you may need to assume that no four sides appear on the same circle. You may assume a general position, but you may get rid of these assumptions later. So we are going to have a Delaunay triangulation, and a Delaunay triangulation is going to be a triangulation of a set of points in 2D plane. So what's the triangulation of a set of 2D points? So given a set of points, we draw edges between these pairs of points, and we get triangles to ourselves. And you can have different triangulations for the same given set of points. There can be there can exist different triangulations. And Delaunay triangulation, which is the dual of the Voronoi diagram, is a triangulation in which the smallest angle in these triangles is maximum among all possible triangulations. In other words, it's like this. Given a triangulation, you look at all the triangles and you maintain the minimum angle in these triangles. In other words, thin triangles or fat triangles. You look at the thinnest triangle in your triangulation. And this minimum angle, you maintain it. And out of all possible triangulations you can have for the same point set, Delaunay triangulation gives you the minimum angle in Delaunay triangulation is maximum among all such possible triangulations. So it gives you the fattest triangles. So there is no thin triangle in Delaunay triangulation. So, and why do we say such a triangulation is a good triangulation? I'm going to give you an example. I'm going to stop here. But when you are given a height map, for example, such triangulations that fat triangles connect neighboring points first. If you have a thin triangle, it means that that triangle is possibly connecting faraway points. And usually, if you're in your triangulation, one of your goals may be interpolating a height map, given heights of certain points on a terrain, given a map as a terrain with as regular heights of certain points. It may be irregular, it doesn't need to be regular, it may be irregular. And your goal may be to interpolate the heights for the parts that are for which the height is not given. And to do that, if you connect two faraway points whose heights may be very different, the interpolation may lead to incorrect results. So putting edges between nearby points is desired in that case. And Delaunay triangulation happens to be the most accurate. The dual graph of Voronoi diagram gives you the best, the optimum triangulation of such point sets. Okay, so and it can be found by first computing the Voronoi diagram and just taking the dual graph of the Voronoi diagram easily. So in 1 log n time, you can compute a Delaunay triangulation as well. But there are other algorithms to compute Delaunay triangulation other than Voronoi diagrams. I'm not going to discuss this in this class. There's a randomized incremental algorithm for Delaunay triangulation. But in the context of this class, the only solution you need to know is just compute the Voronoi diagram first and then do the Delaunay triangulation as the dual graph. Okay? So that's it for today, and no homeworks for